No, okay, now we would say that a doublet is interlaced if it is interlaced all over. And then, okay, so those are, let's say, sets of those double interlaced doublets, and we call it TD sub 2n plus 1, doublets, 2n plus 1. Now, if it is interlaced, I sub 2n plus 1, no problem. And no, and D for D, I for I, and N for normalized. Okay? Now, we have a special, now when A0, the very first integer of the permutation is 0, we add a 0, right? Okay, and all, so D is for all double, I for the interlaced, and for the normalized, I add a 0 whenever A0 equal to 0. Okay, now that's what I started with. Now we are going to play a game. We can act on each double by permuting the kth row. And let's call it a flip, a microflip. Okay, so we have an action now on all permutation by those microflips. And you know, you have read, you know, it's obvious that all those microflips commute. And so microflip means that we permute the two entries in the column number k. And we would say that two doublets are equivalent if we can go from one to the other by playing with the microflips. So if there is sequence phi sub I 1, phi sub I 2, phi sub I k of microflips such that the second one is equal to this product of delta. That's okay. I mean, that's it. So in other words, we can define an equivalence relation on all the doublets. So, okay, now next. So now, I think that this would take this. You would say that every doublet equivalent to the interlaced doublet is also interlaced. It's more or less evident. More or less. We have to sit down and prove it. So in other words, if we define this concept of interlacedness, then a doublet which is equivalent to if a doublet is interlaced, then any doublet in the same equivalent class will also be interlaced. It's not true for the normalized. It's not true for the normalized. So each equivalent class, okay, remember this means that A0 equal to 0. So we are just, and each equivalent class of interlaced doublets contains necessarily 2 to the n doublets. Okay, and then finally, each equivalent class contains one and only one normalized doublet. It's not quite obvious. We have to sit down and prove it. So all this is, you know, the normal work of a mathematician to prove trivial lemmas. And accordingly, we have, so the number of interlaced doublets starting with 0 is equal to 2 to the n of the normalized. So let's, okay, now let's do it very quietly. First, for n equal 1, 2n plus 1. There is only one normalized, you see it? Or this we can do it, huh? There is only one possibility. But 0 must be here. So what I can do, I can only have 3 in here. So, and this is 3, 2, 1, 0 is decreasing. There is only one possibility. And the second one, you see, you just apply phi 1. And it is interlaced. So for n equal 1, There's one normalized, one interlaced. So with this we can make the exercise. For n equal to 2, there are already very many. 2n plus 1 equals to 5. So there are already 4. There are already 4. So and then okay, so with the for the interlace, that's easy because you know. Oh, I'm sorry. I go too fast. Okay. 2 lies between 0 and 5, 0 and 4. 3 lies between. Take this one. 2 lies between 0 and 3. 4 lies between 0 and 5. So we have. And then we have to verify here, there are 4 normalized. And these were written in this tableau because, look at this one. What we have doing here, we have flipped the second column. Here we have flipped the third column. And here we have flipped number 3, number 2, number 3. So we started in each case from one normalized doubloon, and we applied the microflips to the second column and third column. So 1, the 2 together, here is 16. So let's try 1, 2, 16. It's not enough in slow to guess what kind of sequence it is. But anyway, 216. Oh, I give a hint. The next one would be 272. And here it would be 34. Okay. Is it sufficient for Sloan? I don't believe. We need the next one. Next one will be 7936. So, we have a classical sequence coming in. Okay, for 2n plus 1, for n equal 1, so we have for 3, 5, 7, 9, 11. The number of normalized is 1, 4, 34, 496. Oh, this is sufficient for Sloan. If you type this in Sloan integers, you guess what it says? Those are the tangent numbers, the coefficient of the Taylor expansion of tangent. So here, let me say this right away. This is the coefficient of U3 divided by 3 factorial in the Taylor expansion of tangent. This one's 16, and those have higher, very high powers of 2. And this one is simply, that one is simply this one divided by 2 to the n. So now we have to explain why, doing these doubloons, we recover the tangent numbers.
Would you, what if you look for the simpler one in the middle in Sloan? Would that show up directly?
If
you look for the simpler sequence in the middle, would that show up in Sloan?
This one?
The middle one, yeah.
The middle one. This is tangent divided.
Yeah, so that
square root of tangent. It's a square root of 2 tangent of u divided by 2.
So that would show up.
It's called the, yeah, of course. It's called the.
It will show up now, but not before they did it.
Yeah, that's true. That's true. That's true. Good point. Good point. That is true. Yeah.
Thanks to them.
Okay.
Yeah.
Indeed, of course. But that's less known. You see, on the tangent. Yeah. Okay. Okay. So we have this theorem. The number of interlaced doubloons starting with 0 is equal to 2 to the n, the number of normalized terms. First, okay. And now, okay, so we want to work out.
Theorem or lemma?
Oh, that's